Now, just remember with the books in the back table, Christmas is coming. And so if this is your first night here and you were looking at some of the library packs back there, if the books are not totally all available there, what you can do is the ladies will charge you for that and then take down your information. As long as you do it here, and you can actually have that shipped to your house. So you can still get a hold of the deal and get all the material. You just have to purchase it here because it will not be available on the website, just so that you're aware of that. All right, so just so you know, I'm probably full up with questions for the Q&A, unless you come up with a really good one. Had quite a bit, even had one online just a few minutes ago. So we'll be starting that after this next session. So without any further ado, Dr. Lisle.
All right, we're going to talk about the James Webb Space Telescope, some of the discoveries that it's made. I'll warn you that there is a little bit of technical information in this, but I'll try to keep the cookies on the bottom shelf, and you can tell me later if I succeeded or miserably failed. So, but I think this is really amazing what this space telescope has discovered. It strongly confirms biblical creation. I think this will encourage you. It certainly has encouraged me. Not that I had any doubts, but it's just fun. It's just fun to see new discoveries that confirm the Bible. I'm not remotely surprised by them these days, but it's still fun to see. So what I want to do is talk about this telescope. It looks like that. It is an amazing spacecraft. It cost $11 billion. It was funded by your tax dollars. Thank you. It was designed to peer out farther in space than any other telescope can see. And that was supposed to give us an idea of how the universe began. A lot of the folks who constructed this, not all of them, some were creationists, but a lot of them were secularists who believe in the Big Bang, believe our universe is an accident that exploded into existence 13.8 billion years ago. And then this spacecraft is supposed to give us clues onto how the universe, some of the details of the Big Bang. It was supposed to confirm the Big Bang, refute creation once and for all. It turned out not to do that. That's what's exciting about this. And what I want to do is begin by giving you some of the history of this. And I'll start with the predecessor to the Webb telescope, the Hubble Space Telescope, because most people are familiar with the Hubble. And I guarantee you've seen pictures from the Hubble. If you've looked anywhere online, these amazing, beautiful pictures that you see of the night sky, with the ones that are super sharp and have no blurring, those are primarily from the Hubble Space Telescope. So that's what I'll start with, and then I'll show you some of the similarities and differences. Webb is different from Hubble. It has some similarities, but it's different. It's better than Hubble in many ways, and we'll see why that is. Here's the Hubble Space Telescope. It's in low Earth orbit, so it orbits about 300 miles above the surface of the Earth. It was launched in 1990. It was named after Edwin Hubble. He was an astronomer who discovered that galaxies are moving away from each other and from us, that the universe is apparently getting bigger as the galaxies spread out. The Hubble Space Telescope has a 2.4 meter primary mirror that's 7 foot 10 inches. Now I'm 6'1", so the mirror is wider than I am tall, okay, by quite a bit. So it's big. But there are much larger telescopes than Hubble on Earth, much larger. There's some that, would go from here to the wall. I mean, that have a mirror that big. And the bigger the mirror, the brighter stuff looks, the easier it is to get images, the sharper they look. What makes Hubble so good? It's in space. That's what makes it good. And it's not that it's any closer to the stars. It's only 200, 300 miles up. It's not significantly closer to the stars, but it's above Earth's atmosphere, and that's what makes it superior. Earth's atmosphere creates a blurring effect. You've probably seen this if you've looked down the road on a hot summer day, and it looks like it's wavering a little bit. That effect is very strong on a hot summer day looking down the road because you have a lot of atmosphere there. But it's also higher up in the sky. You just don't see it as much. But when you look through a telescope, you see it. If you've ever looked through a telescope on Earth, you'll see the stars. They seem to kind of dance around a little bit. They look a little bit fuzzy. All images of galaxies before 1990 looked a little bit fuzzy. I don't care how great the observatory was, they look a little bit fuzzy. But then after 1990, you started getting these crystal clear images of galaxies, unlike anything we'd seen before. It was wonderful. And not immediately after 1990, because when they first launched it, it was blurry, because they had made a mistake in the machine that was designed to correct the curvature, to test the curvature of the mirror. They had made a little mistake in that, it's a tiny mistake, but the initial images from Hubble were blurry, and the taxpayers were like, oh, come on. And they were able to fix it because Hubble is in low Earth orbit, which means we can put astronauts up there, because we can put astronauts in low Earth orbit. The International Space Station is in low Earth orbit, and we send astronauts up to that and back, and sometimes get them stranded there. That happens. This happened recently. But with the space shuttle, of course, the space shuttle was still in operation when the Hubble was up, so the space shuttle put it up. The space shuttle has an arm that it can release the Hubble, and it can hold on to it, and astronauts can get on there and work it. So when they discovered that it had a problem, they built an instrument that basically acts like glasses to fix Hubble's initially blurry vision. They called it CoStar, and they installed that. Hubble has 4 different instruments in it. It's got one mirror, but it shares 4 different instruments, and they are swappable. Hubble has been upgraded many times since it was launched. Every now and then they'll send astronauts up and they'll take one of the old instruments out, put a new one in, a new better one in. Pretty neat. Upgradable. That's interesting and significant because the Webb telescope is not upgradable. Hubble is fixable. If something goes wrong with it, they can send astronauts up and they can fix it. Webb is not fixable because it's much farther out in space. It's farther out in space than human beings have ever gone, and currently beyond our technology to send human beings that far into space. We've only gone as far as the moon. Webb is farther than that. Anyway, so the Hubble has certain advantages because it's in low Earth orbit. It's upgradable, it's repairable. That's pretty neat. Hubble has about the same wavelength range as the human eye. We can only see certain frequencies of light. We can see, red on this end of the spectrum through yellow, and then violet on this end of the spectrum. And light that has a higher frequency than that, to us, it's invisible. We can't see it. Ultraviolet light, can't see it. And there's also light that has a wavelength that's too long for us to see. That's called infrared. So we see only a narrow section of the spectrum. That's why when you look at a rainbow, it's this thin, right? You look at a rainbow in the sky, and it looks like that. If you could see all frequencies, it would fill the sky. You could see all these other colors that we can't perceive, and colors that go beyond violet. Hubble sees about the same range as we do. It can go a little bit into the ultraviolet and a little bit into the infrared. It's a little bit broader than our vision. And that's very significant. We'll see why that's an issue and why the Webb's different. Webb is designed to look in infrared wavelengths, and we'll see why that is in a little bit. So Hubble sees kind of what we see. And so a lot of the images that Hubble takes are what you'd see if you were there. And that's the neat thing about Hubble. It shows us the way the universe really looks, or how it would look to our eyes if our eyes could gather in more light, basically. Now, it doesn't have to do that. Sometimes they'll use narrow band frequencies, and they'll assign an arbitrary color to them, and you'll get images like this one. This is part of the Eagle Nebula. It's called the Pillars of Creation because they think stars are forming there. They're not, but that's what they claim. And now I've seen the Eagle Nebula. The Eagle Nebula is red. It's not green and all these other shapes. This is an example of artificial color. Sometimes they'll do that. They'll use what are called false color images. They're not doing that to be deceptive. They're doing that to do science. They've assigned each color a certain frequency, and that tells them something about the composition and temperature of what's going on in that nebula. But many of the images from Hubble, like this image of Saturn, are true color. They're basically what your eyes would see. That's the way Saturn looks. I've seen it in a telescope. Now, my telescope image is blurry, but that's what the colors are. That's what Saturn really looks like. So Hubble sees what you see. It just sees it a lot better because it's in space and it's big. Imagine having an eyeball this big, right? You could see quite a bit. You could see stuff that is very faint would become very bright. And of course, it can magnify and zoom in on these things. So Saturn, even though it's very small in the sky, it can zoom in on it, and you get these wonderful images. Being above Earth's atmosphere is what gives it such crisp, clear images. It allows us to zoom in more than an Earth-based telescope. Earth-based telescopes, by the way, there's a common marketing gimmick. You go to Walmart and you see this telescope can magnify 500 times. I got news for you. Any telescope can magnify any number of times. It's just a question of how blurry it'll be. The more you zoom in, the blurrier it gets. Bigger telescopes allow you to zoom in more and keep it sharp, you see. But even there's a limit because of Earth's atmosphere. Hubble is above that. And so when you have images like this, that's a Hubble image of the Whirlpool Galaxy. That's a collection of 100 billion stars out in space, and it's stunning. And before 1990, we didn't have images like that. I mean, I've seen images of the Whirlpool before 1990, but they would always have a little bit of blurring in the stars. That is just as crisp as can be. And that's one of the things that made the Hubble such a superior spacecraft. And it's still working. It's still operational and still taking images. So now in the early 90s, they pointed the Hubble Space Telescope into a section of our galaxy that's relatively empty to see what lies beyond. Small section close to the Big Dipper, and it's kind of empty in our section, so what lies beyond our galaxy? And they found thousands of other galaxies at distances out in space that are just amazing. And that's what's called the Hubble Deep Field. And it goes out to, well, I should explain that galaxies, the farther away they are, their light gets redshifted. It gets shifted toward the red end of the spectrum. That doesn't necessarily mean the galaxy looks red, but it means that when you analyze, when you break the light into a spectrum, a rainbow basically, you'll find that certain colors are missing. And those colors that are missing indicate the element that made the light. It's like an atomic fingerprint. That's how we know what stuff is made of in space. Everything that gives off light leaves an atomic fingerprint by certain specific colors that are missing, and those correspond to the electron levels in the atom. It's amazing. There's a whole field called spectroscopy that deals with this. But we'll find that galaxies that are far away in space, for whatever reason, their light, that atomic fingerprint gets shifted toward the red. It doesn't mean the galaxy looks red overall. You can't tell just by looking at a galaxy if it's redshifted or not. You can't tell. You got to break the light into the spectrum and look at the fingerprint, and if the fingerprint is shifted to the red end of the spectrum, then that tells you that galaxy is far away. Now, some of these galaxies are shifted out to they're a redshift of 6, which means the light has been lengthened 6 times. So they're really far out in space. That corresponds to a distance of about 12.8 billion light years. A light year is a unit of distance. 1 light year is equal to about 5.88 trillion miles. So 12.8 billion times 5.88 trillion, that's a lot of miles. Okay, it's really far out there. That's the point. It's really far out there. Now, in the secular view, light takes 1 year to travel 1 light year. And so if something is 12.8 billion light years away, that means in order for us to see it, the light would have had to have left 12.8 billion years ago. And if you're a creationist, you say there's a problem there, and there is. I would reject that interpretation, and I'm not going to go into the details on the alternative, but nonetheless, for the sake of argument, in the sense of answering the fool according to his folly, I'm going to temporarily say, okay, for the sake of argument, I'll accept that. Those galaxies, therefore, in your view, are 12.8 billion years old, which means they're only 1 billion years after the universe exploded into existence. They're 1 billion years after the Big Bang, some of those galaxies that you see there. But wait a minute. Galaxies are supposed to take time to form. In the secular view, the universe bangs into existence 13.8 billion years ago. It's way too hot to have stars in it. All it's got is energy, pure energy, and then eventually atoms form. And then stars form from those atoms, and that takes hundreds of millions of years. And then the stars collect into galaxies. That takes hundreds of millions of years. And then the galaxies collide with each other and become these beautiful spirals over time. Which means in the secular view, the farther out you look into space, you should see things not as they are today, but as they were in the past. And if you look out far enough, you shouldn't see any galaxies at all, because they haven't formed yet. And so it was a bit of a surprise when they looked back that far into space at a distance that, in their view, corresponds to a time less than 1 billion years after the Big Bang, and they're seeing fully formed galaxies, almost as if they were just spoken into existence by God, rather than having evolved over billions of years. That's interesting. Well, we haven't gone out far enough. That's the problem, right? The problem with Hubble is it doesn't go far enough. So they pointed it even, they time exposed it even further. They pointed it out into a region of space that's even deeper, called the Hubble Ultra Deep Field. And they found more galaxies. But wait a minute, the galaxies should stop at some point, because in the secular view, you're looking back to a time. Eventually, you'll look far enough back to a time when they haven't formed yet. But there's still plenty of galaxies there. We must not be looking out far enough. That's one of the main motivations for the development of the James Webb Space Telescope, to be able to look farther than Hubble, and it can. It can look much farther out in space than Hubble can. And so the idea was, we'll finally look out to the distance where galaxies stop, because they hadn't come into, you were looking back to a time where they hadn't come into existence yet. Keep that in mind. That's one of the main motivations, not the only one, that's one of the main motivations for the development of the James Webb Space Telescope. But the Hubble Space Telescope can only see so far in space. Why is that? It has to do with these redshifts we've been talking about. Edwin Hubble, he was an astronomer. In the 1920s, he started measuring the distance to galaxies, and he'd also measured their velocity by measuring that redshift. You see, if something's moving toward us, the light gets shifted toward the blue. Doesn't mean the galaxy looks blue, but the galaxy color is unaffected relatively, but it means those spectral lines are shifted toward the blue end of the spectrum. Whereas if a galaxy is moving away from us at high speed, those lines get shifted to the red end of the spectrum. That's the Doppler effect. You can hear the Doppler effect when a car goes by, right? And when it's moving toward you, the pitch changes. You've heard that. That's the Doppler effect. It's easy with sound because the speed of sound is only about 700 miles per hour. And so a car that's going 70 miles an hour is going 10% the speed of sound. And so that's pretty fast. And so you can hear the pitch change. With light is a lot faster. Light moves at 186,000 miles per second. Is fast. And so if you move a light bulb toward you, it doesn't look any bluer. If you move it away, it doesn't look any redder. But if you could move it fast enough, the light would change. It would change color. And you can detect that by those spectral lines, you see. That's what Edwin Hubble was doing. He was measuring the spectral shift in those lines, and he found out, you know what? Just about all galaxies are redshifted. Which means they're all moving away from us. And the really weird thing is, the farther away a galaxy is, the faster it's moving away from us. That's what that line represents. So that's the velocity of the galaxy on the vertical and the distance on the horizontal. And you plot it, and sure enough, the galaxy, there's some scatter, but for the most part, the galaxies that are really close to us have a low velocity. They're moving away from us slowly. The galaxies that are far away from us are moving away from us quickly. It's as if the entire universe is being stretched out or expanded, just like the Bible says in Isaiah 40:22, by the way. The Bible predicted that. Interesting. Now, what does this have to do with Hubble? What it means is there's a limit as to how far Hubble can look. Normally, when a galaxy is moving away at high speeds, those lines, they're redshifted, okay? But the overall color of the galaxy doesn't change very much because the colors that were visible, they get shifted to the infrared and you can't see them anymore. But the galaxy is also giving off light that's in the ultraviolet, and it gets shifted into the visible. And so the galaxy looks about the same. It's just the frequencies that were here get shifted here, and the frequencies that were here get shifted there, but the overall color that we can see in the visible range stays about the same, up to a point. Because it turns out that frequencies of light that have a wavelength shorter than 911 angstroms have so much energy that hydrogen atoms can absorb them. They can absorb that light. And so the bottom line is galaxies don't give off light beyond a certain range in the ultraviolet. That's called the Lyman limit. And so beyond that, they don't give off light. So what happens when a galaxy is so redshifted that the Lyman limit goes below our visible spectrum? The galaxy becomes invisible. We can't see it anymore. All of its light has been shifted to frequencies that we can't see. And as I mentioned earlier, Hubble sees kind of what we see. It has a little bit larger range than we do. But what that means is there's a redshift beyond which Hubble cannot see because all the light has been shifted out of its ability to detect. It's down here in the infrared, and Hubble can't see in the infrared. So there is a limit, there's a distance at which galaxies are so redshifted, Hubble can't detect them anymore. Hubble can only see so far in space because of this Hubble law, the fact that galaxies that are farther away are more redshifted. That's why the James Webb Space Telescope was developed and launched. It was actually launched in 2021, but it came online in July of 2022. It was designed to see these wavelengths down here in the infrared that we can't see at all, and Hubble can't see. But galaxies that are far away, their light's been shifted down to this end. James Webb can see them. Hubble can't. That's why it was developed. It's designed to see galaxies farther away than anything else that we have. It was developed, believe it or not, in the 1980s. The first mention of this, they were calling it the Next Generation Space Telescope. The Hubble successor was being planned in the 1980s. Yeah, that's how science works. It just takes that long sometimes. So even before Hubble wasn't launched until 1990, but even before it was launched, scientists were already planning its successor. Got to think ahead in science, especially when you're getting funding from the government. You have to think ahead. So they were calling it the Next Generation Space Telescope. I remember talking about this when I was in grad school. I was in my instrumentation class. This would have been 1998. And we were all excited about this Next Generation Space Telescope. It didn't have the name yet. And how exciting that. We were bummed that we had to wait until 2007 for it to launch. Of course, it wasn't until 2021. But again, that's a government project. So there you go. But I actually know people who have designed portions of this spacecraft, and it is a masterpiece of engineering. I'll go through some of the details of how it was built. It is brilliant. And the people that built it are brilliant. They really are. And I'm very proud to know some of those folks, and I congratulate them on its success, because the James Webb is not serviceable. It's out much deeper in space than the Hubble. And then eventually, it would be named after James Webb. He was a director of NASA. It was in 2002 they decided to name the telescope after James Webb. He was in charge of NASA from 1961 to 1968, and in my view, those were kind of the glory days of NASA, because that's when they were designing the Apollo program, where we were going to land people on the moon. And James Webb was responsible for getting a lot of the funding to make that program happen. So if you're happy that we landed on the moon, you can thank James Webb, among other people like Wernher von Braun and so on. So he passed away in 1992. From everything I read about him, he seems like he was a really good guy. A lot of the leftists did not want the telescope renamed in honor of him. In fact, there was a campaign against him because he had a problem with people who were sexual perverts working at NASA. And the people who are perverts today didn't like that, and so they wanted NASA to change the name. And NASA said, no, we're sticking with the name, so good on them. But anyway, so that's the person the James Webb Space Telescope is named after. James Webb Space Telescope is much bigger than Hubble, much bigger. So there's a person for scale for the Hubble's mirror, and then there's the James Webb Space Telescope mirror. Impressive. It is big. And you want that in astronomy. In astronomy, bigger is better. It is, because it gives you more light gathering power. It allows you to see fainter things, and it makes faint things bright. That's the main thing telescopes do. They do magnify, but that's not the main thing. They make faint things bright, because they take all that light. A telescope that you would get on Earth takes light from whatever the size of the mirror is and squeezes it down so it can fit into your eyeball. That's what telescopes do. They make faint things bright. So you can imagine how bright that would make things. So, and in fact, it's so big, they didn't make a single mirror that big. They decided to make it out of 18 hexagonal sub-mirrors, each one of which is pretty big. And the reason they did that, one reason, that won't fit in any rocket we have. And so what they did is they designed the outer layers to fold back, so that it actually folds and then fits in the rocket, and then it unfolds once it's in space. Brilliant. And the sun shield on it, too, is designed to fold back, and then it unfolds in space. Amazing. So it's bigger than Hubble. Hubble's mirror is 2.4 meters across. That's, again, 7 foot, 10 inches. Webb is 6.5 meters across. That's 21 feet. That's the diameter of the mirror, so it's huge. And that means it's got a lot more light gathering power than Hubble. You'll also notice the color's different. That's because the Hubble mirror is covered with a thin layer of silver. Silver is great for reflecting the frequencies of light that we can see. And so most telescopes are coated either with silver or aluminum. But if you want to reflect infrared light, silver's not the best. Gold is better. And so the mirrors of the James Webb Space Telescope are covered in a thin layer of gold, about 800 atoms thick. And it's the plates themselves are made of beryllium. That's a nice, very light metal. And the nice thing about beryllium is it doesn't expand or contract as much as most metals do. It does somewhat, and they had to calculate that. And again, it shows you how much thought went into this. You know, metals expand when they're hot and they contract when they're cold. Beryllium does that too, but it'll only contract to a certain point and then it stops. And so that's a nice metal to work with. But when they built this thing, they intentionally made those beryllium mirrors a little too big on Earth, so that when it's in space and cools, they will contract to the right size. That just gives you some of the thought that had to go into this. That's pretty amazing, I think. So it's a brilliantly designed spacecraft. It is designed to operate in the infrared frequencies. Hubble sees kind of what you see. It sees these visible wavelengths of light. Hubble can go a little bit into the ultraviolet, a little bit into the infrared. James Webb goes deep into the infrared. And that's what we want, because the galaxies that are far away, their light has been shifted to the infrared. It's been redshifted. So that's what we want, to see distant galaxies. And I think it has it's got the measurements there. So pretty neat. And that's why you have that gold plating. So that's what it looks like. The mirror, you now know what the mirror does. The mirror brings the light to a focus, and then there are instruments that can detect that, and they can detect infrared wavelengths of light. And then, of course, below the mirror, you have this big silver structure. That's a sun shield. It's got multiple layers. It unfolded in space. It's about the size of a tennis court. Remember, this thing's big. And again, I know people who actually designed that sun shield. It's pretty amazing the way it unfolds. And that's needed because this spacecraft has to be very cold to operate properly. There's a reason for that. Hubble doesn't have to be. Hubble is the temperature that it is, and it works perfectly fine. Webb has to be cold. Why? Well, we emit electromagnetic radiation. It's just you don't see it because the electromagnetic radiation we give off is in the infrared part of the spectrum below what we can see. But if I gave you thermal goggles that turn infrared light into regular light that we can see and turned off the lights, you'd all be glowing. And maybe you've seen that on the television. You've seen people with those thermal goggles, and you can look at animals or human beings and we're glowing. We're giving off light because we have a positive temperature. Everything does that, and the cooler it is, the less it does it, and the lower the frequencies of those light. But everything gives off infrared light. So if this telescope were to try to operate at room temperature, it would see its own glow because it's designed to see these wavelengths, but it's giving off those wavelengths, so it would see itself. That's all it would see. It'd be like trying to do astronomy in the day when you have all this light around. It's very difficult to do it. So they need to get this instrument very, very cold so that it doesn't give off its own light and see nothing but itself. So they had to do a lot to get that to work. And the detectors, frankly, the detectors work best when they're cold. Detectors have what's called dark current, but the colder you get it, the less dark current they have. It adds kind of like a layer of static to any image you try to take. But if you get it cold, then that reduces that. So let's see if I have the numbers here. Yeah, so for the James Webb Space Telescope to work properly, it needs to reach a temperature below 40 kelvins, which is negative 370 degrees Fahrenheit. So if you thought it got cold here, negative 370 degrees Fahrenheit. Think of that the next time you get snow on your car. So that's pretty cold. And that multi-layered sun shield is designed, that always is pointed toward the sun. So the sun would be below the spacecraft in this image. So the shield always is between the sun and the mirror on the spacecraft, and that allows it to cool off in space because it's not getting any sunlight. And they put it in a location in space where it's going to be far enough away from the Earth that it's not going to get Earth light either. So, pretty amazing, really. And they had to do all kinds of tests on it because, you build this circuit and you say, that works pretty well. It works well at room temperature. Will it work at negative 370 degrees Fahrenheit? Because some circuits won't. Certain transistors stop working when you get them that cold. So they had to test the technology and see which transistors will work at that temperature. Pretty amazing, really. Now, the James Webb Space Telescope has 4 different detectors on it. 1 mirror, 4 different instruments that can detect different ranges of infrared frequencies. And 3 of them operate well at 40 kelvins, which is the temperature the spacecraft needs to come to after it sits there in space for a while and cools off, basically. As long as you get that sun shield between the sun and the mirror, it'll do that. The remaining instrument, which is called MIRI, operates so far in the infrared that it needs to be even colder. And so they have a system, they have an active cooling system on it, basically an air conditioner on it, because negative 370 degrees isn't enough. It needs to be even colder than that. It has to get down to a temperature of 7 kelvins, which is negative 447 degrees Fahrenheit. That's how cold it has to be for that instrument to work properly. So it is an engineering marvel. It really is. You can't just put it anywhere. You can't put it close to the Earth. Hubble's in Earth orbit. Can't put James Webb in Earth orbit. Why? Because the Earth gives off heat. It would heat up the spacecraft too much. So what they did was they put it at what's called the L2 Lagrange point. There was a mathematician, Lagrange, who figured out that there are 5 locations relative to the Earth and Sun where you could place an object. If you give it just the right speed, it will orbit at the same revolutional speed as the Earth. So it'll maintain its position relative to the Sun and the Earth. There are 5 of these locations. They're indicated by L1, 2, 3, 4, and 5. And the James Webb Space Telescope is at L2, which is beyond the Earth. It's about 1 million miles into space beyond the Earth, the opposite direction of the Sun. And so not only does the sun shield protect from the sun's heat, but also the little bit of heat that the Earth gives off as well. So that means it's not accessible, it's not repairable. When they launched it, if something had gone wrong, that would be $11 billion down the drain. Fortunately, it worked, so we were all real happy about that. An amazing spacecraft, and it can see deeper into space because it's designed to look in these frequencies that galaxies have when they're very far away. Far galaxies are redshifted because they're moving away from us very quickly, so their light's been shifted from the range that Hubble can detect, that you could see. They'd be invisible to us, but the James Webb Space Telescope can see them because it sees these lower frequencies of light, these infrared frequencies. Now, secularists made a number of predictions about what they were expecting the James Webb Space Telescope to find based on their belief in the Big Bang in the billions of years. And here's what they were expecting. They were expecting fewer galaxies at great distances and none beyond a redshift of 14. Why? Well, remember, in the secular view, as you look out farther into space, we know the redshifts get deeper, but in their view, as you look farther into space, it's kind of like looking back in time because you're seeing the galaxies when the light was emitted, which they believe was billions of years ago. So if you look out beyond a redshift of 14, that corresponds, in their view, to a distance and a time where galaxies haven't formed yet. So they believe you're looking back in time, and you should see a time where there aren't any galaxies. And of course, before you get to that, you should see relatively few galaxies, right? Because you're looking back to a time when there were only a handful of galaxies in the universe, because it takes time for those galaxies to form as the stars form and collect into the galaxies. And so you'd expect to see very few at a redshift of 14 and really none beyond that. And the farthest galaxies you do see ought to be babies. Low-mass, clumpy galaxies that have just formed. So, the idea is that when galaxies first, they start with a few stars, and then more stars get added, and then they collide with other galaxies and gather more stars. They get more and more massive, and they become more well-structured over time. And so these beautiful spiral galaxies, those are thought to be relatively recent. The early universe shouldn't have those. The very earliest universe should have no galaxies, and then as you get a little closer, you have a few, but they're baby galaxies, low mass, clumpy, and irregular. Finally, they expected that these farthest galaxies would have no what are called heavy elements or metals. Now, in astronomy, a heavy element's anything beyond the first 3. So if you look at the periodic table, you got hydrogen, helium, lithium, everything else is a heavy element in astronomy. And the reason for that is the Big Bang is supposed to produce the first 3 elements, hydrogen, helium, and lithium. The Big Bang is supposed to start with pure energy, and as it cools, those elements form, but the conditions aren't right to form any other elements. The temperature and density are such that you can only get hydrogen, helium, and just trace amounts of lithium. None of the heavy elements are supposed to be made by the Big Bang. But we do have heavier elements in the universe. We've got oxygen and carbon, stuff that we're made of. So how do the secularists account for heavy elements? Well, they would say that stars make the heavier elements in their core. But only the largest stars will do that. The very largest stars, they have such a high temperature and pressure in their core that eventually they're able to fuse and synthesize the heavier elements, oxygen, carbon, and eventually things like iron and so on. And then when these stars explode, which does occasionally happen, they spread those elements out into space, and so the next generation of stars has a little bit of these heavier elements in it. That's the idea. So the idea is the first generation of stars should have only the lightest elements, right? If the Big Bang can only make hydrogen, helium, and lithium, if the only thing in the universe is hydrogen, helium, and lithium, when the first stars form, what would they be made of? Hydrogen, helium, lithium. That's it. There isn't anything else. So the first stars, which would be called, if they existed, they'd be called population 3 stars, should have no heavy elements at all. No oxygen, no carbon. And then the next generation of stars, When some of those stars explode, they make the heavier elements in their core, and then they explode. Then the next generation of stars has more heavy elements, and then the third generation has even more. So those would be population 2, population 1. It goes backwards because of discovery reasons. Anyway, farthest galaxies should have no heavy elements because they haven't had time to form yet. Those are the secular predictions. You got it? Look far enough, you'll see a time when there were no galaxies. You look close to that, you'll see very few, and they ought to be baby galaxies, clumpy and irregular. And the galaxies that you do see, those far ones, should have no heavy elements. But that's all based on the Big Bang. I don't believe the Big Bang. I believe in biblical creation. And so I thought, you know what, I'm going to make some predictions too. And so back in January of 2020, I wrote down my predictions. I published them. My predictions are basically the opposite of these. And I'll tell you why that is. I predicted that we'd see lots of galaxies, even at great distances, even beyond redshift of 14. Why? Because I don't believe we're looking back in time. I believe we're seeing the universe as it is, according to the definition the Bible uses of now. And so I don't think God stopped creating galaxies at a redshift of 14. I don't think we're looking back in time toward a Big Bang. I think we're just seeing galaxies at greater and greater distances, and I don't see any reason why God would stop at a redshift of 14. I think he continued to make them, probably forever. So I believe in lots of galaxies, even at great distances beyond redshift of 14. I don't think they'll taper out. I think they'll keep going. And the galaxies that we do see, the farthest ones that we see in the James Webb Space Telescope, they won't be baby galaxies. I don't believe in baby galaxies. God made Adam and Eve as adults. I believe he made the galaxies as adults. When God made the stars also on day 4 of the creation week, he made them pretty much like they are today. Some of them have exploded since then, but the farthest galaxies will be fully formed, which means they'll be massive and well-structured, like nearby galaxies. Not baby galaxies, not clumpy and irregular, okay? And I believe the farthest galaxies will have heavy elements. Why? Well, I have an advantage. I have the history recorded in the Bible, and I believe it. That gives me an advantage. I know from Scripture that not all heavy elements were formed in stars. And by the way, I do think it's possible for the largest stars to produce heavy elements in the core. I think there's some good science there. But see, secularists believe all heavy elements were made that way, including the heavy elements that make up the Earth. You might have heard secularists, Carl Sagan or Neil deGrasse Tyson, say, we're all made of star stuff. That's what they mean. They mean the elements like oxygen and carbon that make up our bodies were forged in the core of a star. But I know better, because I know the Earth was made before the stars were. Earth's made on day 1. According to Scripture, stars are made on day 4. Is Earth made of star stuff? No. Earth was here before the stars. And I know Earth had oxygen in it before the stars. Why? Genesis 1, God created heaven and the earth was without form and void, and darkness was upon the face of the deep, and the Spirit of God was hovering over the waters. So the earth had water on it on day 1. Water is H2O, O is oxygen. So oxygen existed on day 1 when the earth was made. Stars aren't made until day 4. So the oxygen on the earth did not come from stars. It preceded the stars. So I believe that the farthest galaxies will have heavy elements just like the nearby galaxies, because they're made as adults, just like Adam was. And I got to tell you guys, I believe the Bible, and I have enough confidence in it that I was willing to not only put these claims out there, and these are the opposite. These are the exact opposite of what the secularists were saying. I was so confident that they would be wrong that I even I tried to predict how they would respond when they found out they were wrong. Because what they're going to find is they're going to find galaxies far beyond redshift of 14 where there shouldn't be any because they haven't had time to form yet. I predict that instead of giving up the Big Bang, because that's their sacred cow, they're not going to give that up. What they'll do instead is just push galaxy formation back to an earlier time. They'll say, well, I guess galaxies formed a lot earlier than we thought. So here's my prediction. Secularists will respond to their failed predictions with statements like, Webb discovers that galaxies formed much earlier than previously thought. That's my prediction. So, and you can find these predictions on the website, Biblical Science Institute. The article is the James Webb Space Telescope. This was published January 21st, 2022. This was before the James Webb had taken any data. It didn't release data until July that year. Okay, so this is months before we'd had any results. So what did they find? Well, they pointed the Webb telescope out to a section of our galaxy relatively empty. Did they find that galaxies stop at a certain distance? Here's what they found. Galaxies upon galaxies upon galaxies. How about that? And they're in incredible redshifts, some of them well beyond a redshift of 14. Redshift 16, 18, one of them we think has a redshift of 20. That is way beyond what the secularists were expecting. By their math, that puts it at a time of like 300 billion years after the Big Bang. Galaxies should not have had time to form yet. But there they are, and there's lots of them. How about that? Isn't that beautiful? What you're seeing there, even those tiny little dots you're seeing in the background, those are not individual stars. Those are galaxies with hundreds of billions of stars each. The tiniest little specks you're seeing there, those are galaxies. The distances are outrageous. What are the results of the James Webb Space Telescope data? First of all, lots of galaxies at great distances, even beyond a redshift of 14. Again, some of them out to a redshift of 20. And a lot of those are being debated, but some of them have been confirmed already, so that's pretty neat. What about these farthest galaxies? Are they little baby irregular galaxies? No. Farthest galaxies are fully formed, massive, and well-structured. You can see that in those images. You can see that there are spiral galaxies out there. They're big. They're massive and well-structured. Spiral galaxies. They're not clumpy, irregular baby galaxies. Even secularists have admitted these galaxies are as massive as galaxies nearby. They were not expecting that. They were not expecting that. What about heavy elements? Are they devoid of heavy elements like the secularists expected? No. The farthest galaxies have detectable heavy elements. The James Webb spacecraft has a spectrometer on board which can break the light into a spectrum and identify the atomic elements that made the light. And it's detected heavy elements like carbon and oxygen in these distant galaxies, not the population 3 stars that are devoid of such elements. Pretty neat. So in all cases, the creationist predictions were right. The secular predictions are what we call wrong. They're just dead wrong. What about my prediction about how they would respond? I predicted they would say things like, here's my quote of what I'm expecting them to say. Webb discovers that galaxies formed much earlier than previously thought. How did they respond? Here's a quote. Galaxies started forming much earlier than many astronomers previously thought. That's from Yukon Today, August 9, 2022. You can look it up. Here's another one. Massive galaxies formed earlier in the universe than previously known. Nature News, July 27, 2022. Here's another one. Evidence is building that the first galaxies formed earlier than expected. Earlier than you expected. Not earlier than we expected. That's the Sky and Telescope, January 10, 2023. Here's another one. A lot of galaxies could have been formed in the universe much earlier than previously thought. Space.com, January 12, 2023. I go on and on. I found dozens of these headlines. I was trying to find one that was exactly the way I worded it, but they're pretty close. So it's neat. See, the Bible not only tells me about the universe, which is why I can make these predictions that the secularists can't, it also tells me about human nature and how people respond when they have a cherished cow that they don't want to give up. That's why I was able to predict how people would respond. The Bible tells us about the universe, and it tells us about human nature. So, if you're keeping track, the secularists predicted fewer galaxies at great distances and essentially none beyond redshift of 14. The creationists predicted many galaxies at great distances exceeding redshift 14. The secularists were wrong. We were right. James Webb confirmed that. Secularists, the farthest galaxies would be low mass, clumpy baby galaxies. We predicted farthest galaxies would be fully designed and mature. Secularists were wrong, creationists were right. James Webb confirms that. Secularists predicted the farthest galaxies would have only population 3 stars, no heavy elements. Creationists predicted the farthest galaxies would have population 1 and 2 stars, which do have detectable heavy elements, and those have now been detected by the James Webb Space Telescope. Pretty neat, pretty exciting. By the way, I'd love to use this as an example. If somebody says, well, creationists, they don't make any successful predictions. Yeah, we do. You may not read our literature, but we do. They're there. There's one more exciting aspect I want to share with you before we close out for the evening. And that concerns something that none of us were expecting. And that's always fun. So, I mean, we tend to use science as, see, it confirms creation, and it does. But sometimes God just gives us these little nuggets that nobody was expecting. And I want to share one of those with you. And I published the result of this in the Answers Research Journal, which is a peer-reviewed creation-based science journal. And it's called Sizes of Galaxies in James Webb Space Telescope Data Suggest New Cosmology. This is interesting. There was something I was not expecting that no one was expecting in the James Webb Space Telescope images of these galaxies. You see, normally, Galaxies, the farther away they are, the smaller they look. we understand that. You see a car that's right next to you, it looks big. You see a car down the road, it looks small. That's angular size, how big something looks to your eye. And the farther away something is, the smaller it looks. That is perspective. You move something twice as far away, it will look half as tall, half as wide. We get that. We have everyday experience with that. And galaxies are no exception. They're like that too. If I show you the Andromeda Galaxy in a telescope, it's nice and big. If I show you one that's further away, it'll look smaller. But if the universe is expanding, if the fabric of space is expanding, that creates a sort of distortion effect in light that's traveling through it. Yeah, I need to back up and give a little historical information. We talked about Edwin Hubble. He was the astronomer that found that the farther away a galaxy is, the more redshifted its light is. Farther away, more redshifted. Apparently, the galaxy is moving away from us at high speed. But in the 1920s, 4 physicists had been playing around with the physics that Einstein had just discovered, and they tried applying it to the entire universe, and they found that it was possible that the entire universe, the fabric of space, could itself expand or contract. And so when they found that all the galaxies seemed to be moving away from us, they said, the entire universe is expanding because the fabric of space is expanding, and the galaxies kind of go along for the ride. And the way to picture this is you paint a bunch of dots on a balloon, and then you blow up the balloon. All the points will move away from all the other points, won't they? Because the fabric of the space between them is expanding. And so very quickly, by the 1930s, most astronomers and physicists had jumped on that explanation. They thought, the reason we have a Hubble law, the reason galaxies appear to be moving away from us, it's not because they're moving through space, it's because space itself is expanding. The fabric of space is expanding. We tend to think of space as nothing, but space has properties to it. It can be thought of as a fabric that can be stretched. And those 4 physicists, their names are Friedman, Lemaitre, Robertson, and Walker. And the math that describes this expansion of the fabric of space is named after them. It's called the Friedman, Lemaitre, Robertson, Walker metric. But that's a mouthful, so sometimes we shorten it, just the last 2, the Robertson-Walker metric. That's the math that describes the expansion or stretching of the fabric of space, which is thought to be the cause of the Hubble law. Now, it wouldn't have to be. It could be that space is static and the galaxies are just moving through space, and the farther away they are, the faster they are for whatever reason. But it turns out that if the fabric of space is expanding and light is traveling through that expanding space, it stretches out the light, it explains the redshift, but it also creates a distortion of whatever you're looking at. It causes it to look bigger. It acts like a magnifying glass. Now, I'm not going to go into the mathematical details of why that works, because it's kind of counterintuitive. I'm just asking you to take my word for it that in an expanding space, whatever you look at will look a little bigger than it really is because of the way the light's been bent. And you have some experience with that. You know that when you hold a magnifying glass on something, because of the way it bends the light, the image of what you're looking at looks bigger than it really is. The same effect would happen if space is expanding. And the longer the light's been traveling through that space, the bigger the object will look, which means the farther away an object is, the more magnified it'll be. But we already know that from perspective, if you look far enough, something should look smaller. It turns out that at a certain point, the expansion of space overwhelms perspective and will cause objects to look bigger with increasing distance. So if space is expanding, galaxies nearby will look big, galaxies that are farther away will look smaller up to a certain distance, and then they'll start to look bigger again, like you see here. I was expecting to see this in the James Webb Space Telescope images, because it turns out the distance at which galaxies would look smallest corresponds to a redshift of 1.6. Not that far out. James Webb can go way beyond that. Remember, it can go out to a redshift of 20. So I was expecting these distant galaxies to look much bigger than nearby galaxies, but you don't see that. You don't see that. The farther away the galaxy is, the smaller it looks. It's as if the fabric of space is not expanding at all. I thought, that's interesting. Maybe the Friedman, Lemaitre, Robertson, Walker metric is just wrong. They made some assumptions in that. Maybe those assumptions are wrong. So here's what I'm suggesting. We know this. We know that the farther away a galaxy is, the faster it's moving away from us. Edwin Hubble discovered that. So it's like this. The entire universe is being expanded. There's no doubt about that. That's happening. So it's like that. The normal explanation is that is caused because the fabric of space is expanding and the galaxies just go along for the ride like this. Okay? So it's like the surface of a balloon being blown up and the dots on the balloon get farther apart. But what if the space is not being stretched and the galaxies are merely moving through space like this? That's possible too. So the standard explanation that everyone has assumed since 1929 is the Robertson-Walker metric, that the fabric of space is expanding and the galaxies just go along for the ride. But that would create a magnification effect that we do not see. And so I'm going to suggest what I call the Doppler model, that in fact, space is more or less static. It doesn't have to be exactly static, but the fabric of space does not expand, and galaxies are just moving through space. And the farther away they are, the faster they're going, because God gave them that initial velocity. And I went through the math on this, and the math is not easy, but I was able to work it out. And I calculated how big would a typical galaxy look at a certain distance if the standard model's right versus the Doppler model. And these are the charts. So I took a typical galaxy. The average size of a galaxy is something like 4.5 kiloparsecs. That's kind of the average diameter of a galaxy. And I calculated how big would that look, its angular diameter, at different redshifts, which correspond to distance. At a redshift of 1, you're pretty far out there. So if the standard model's right, the galaxies they look smaller and smaller and smaller out to a redshift of 1.6, which is about right there. And then they start to look bigger again, or they should. They should look bigger and bigger and bigger, and that's how big a typical galaxy should look. On the other hand, if space is not expanding, then that magnification effect doesn't exist. And so galaxies will simply look smaller with redshift, and I calculated how big they should look. And it would just be smaller and smaller and smaller. And just for fun, I also included an old model called the tired light model, which is being revisited. It says that space is not expanding, nor are galaxies moving, but light just kind of loses energy as it goes, and that's the explanation for the redshifts. I don't think that's right, but I included it for the sake of comparison. And then I took the actual data. Astronomers have been looking at these James Webb images and have measured the size of galaxies. Now, galaxies come in a range of sizes, so there's quite a lot. But this should be the average size if the standard model's right. And you can see that all those galaxies are well below that. On the other hand, if the Doppler's model is right, then that is about the average, isn't it? That looks like that's about half of them are above it, half of them below it. So I plotted what is the median, kind of the average, the median size of those galaxies in each bin, and look how where they line up with. So what this is showing you is that the Doppler model correctly predicts the angular size of galaxies at all redshifts, including these ones that are in the James Webb Space Telescope. It shows why they continue to look smaller and smaller and smaller is because the fabric of space is not expanding. Galaxies are simply moving through it. Pretty neat. It doesn't match the standard model at all. Not even one data point matches the standard model. Isn't that interesting? And when I plotted that graph, I thought, oh, we're onto something here. Because rarely in cosmology do the data look that good. I mean, it just confirms the Doppler model almost perfectly. So that was really exciting. And I have to point out, I have made a couple of assumptions, or at least one assumption. I've assumed that a typical galaxy size here is the same as a typical galaxy size out there. Secularists could argue that the reason it looks like my model is right, rather than the standard model, is because galaxies, for some reason, are actually much smaller over there. But that's not a very good explanation because we already know they're as massive as nearby galaxies. How could a galaxy get bigger? How could it just expand without gaining mass? That doesn't make any sense. And they would have to expand in just the right way to make my model look right and the standard model look wrong. So if you're a fan of Occam's razor, that is not a good explanation. So don't get lost in the details. The point is the data line up with the Doppler model. They do not line up with the idea of an expanding universe because we do not see this magnification effect. It's not there. Galaxies continue to look smaller at all distances, which is what you would expect if they're simply moving through a non-expanding fabric of space. So the universe is expanding, but the fabric of space doesn't expand with it. And one of the neat things about that, it means the Big Bang is impossible. The Big Bang requires the fabric of space to expand so that when you run it backwards, it all goes back to a point. If the galaxies are merely moving through space, you'd say, well, wouldn't they go back to a point? No, because they have a little bit of sideways velocity too. So when you run it backwards, they would miss each other. They would just and they continue to expand the other direction, you see. Some galaxies are blue shifted. They're currently moving toward us, so when you run it backwards, they get further away. The galaxies would not go back to a point if the Doppler's model is true, and it is. You can see from the data, it lines up perfectly. I did similar experiments with the brightness of galaxies, because it turns out if space is expanding versus galaxies are simply moving through space, you get two different answers for how bright a galaxy should look. And it turns out galaxies should look fainter if the Doppler's model is true. That's the black line, versus the standard model. The standard model is the red line, and the blue line is the actual data. And you can see the galaxies do look fainter with distance, which is exactly what you'd expect for the Doppler model. So here's the bottom line. The angular sizes, how big they look, of distant galaxies in the James Webb Space Telescope data are consistent with the redshifts being caused entirely by the Doppler effect. They're just moving through space. Space is not expanding according to the Robertson-Walker metric. Furthermore, the brightness of distant galaxies is likewise consistent with the Doppler model and not with the Robertson-Walker metric. This suggests that no substantial galaxy evolution has occurred. Distant galaxies, if you believe the Doppler model, distant galaxies are the same size, same mass, same brightness as nearby galaxies, which means you're not looking back billions of years. You're looking at the way you're just looking at galaxies that are far away, and they're virtually identical to nearby galaxies. That's pretty neat. That's pretty neat. And we already know, secularists will admit, that the structure, mass, and metallicity of distant galaxies is similar to nearby galaxies. So secularists were expecting distant galaxies would be very different from ours because they're billions of years younger. And all this activity, all this chemistry that's happened over billions of years, which should make our galaxy look different from those. That's not what we see. Isn't that exciting? So this is brand new research. This is just this year that this was published. The Doppler model indicates that the Big Bang cannot occur. It can't because it requires an expanding metric. It requires the fabric of space to be expanding, and it's not. The data show that the galaxies are merely moving through space. And so this indicates we now have a new cosmology that's creation-based, and that's very exciting because we can make successful predictions about what we are going to find, and I've already made one. I'm predicting that the James Webb Space Telescope will continue to find galaxies at longer and longer redshifts, and their average angular diameter will be 0.2 arcseconds. Now, that is a very specific prediction based on the Doppler model, and it's 10 times different from what the Big Bang would assume. So you heard it here. You heard my prediction. We'll see in the next few years whether or not I'm right. But this is very exciting stuff. So the Doppler model, it's consistent with the ASK model, if you're familiar with that. If you're familiar with my explanation for distant starlight, they're compatible. They go well together. And it paves the way for future biblical cosmological models. Again, this is published in the literature. I've got a summary article on my website where I've kind of removed the math, basically, and made it a little easier to understand. So you might check that out on the website. And hopefully, having heard it and then reading the article, it'll make a lot of sense. But pretty exciting stuff. So we've already seen that we creationists have made correct predictions about what James Webb would detect. Remember, we predicted the galaxies would be farther away than the secularists were predicted, that they'd be big, massive, and well-structured. The secularists were predicting baby galaxies that are irregular, and we predicted metals, and those have already been found. We're right on those. And here's a fourth prediction. We're predicting the sizes of these distant galaxies will be 0.2 arcseconds instead of 2 arcseconds, a factor of 10 larger. So we're predicting that as well as a future observation. So check back in a year or two, and we'll see if we're right about that one. But very exciting time to be a biblical creationist because we're now leading the way in cosmological research. That's cool. If the secularists don't get on board, they're going to get left behind. We're going to be the ones making all the correct predictions, doing science, and the secularists will just be sitting there trying to come up with explanations for why we're wrong. So, pretty neat. Again, you can check out our resources. Taking Back Astronomy will go through some of the basics of what I talked about. It won't go through this new research because this is brand new, but it goes through some of the basics of astronomy and how that confirms biblical creation. And we have DVDs on that as well. And of course, Stargazer's Guide to the Night Sky, how to better enjoy the night sky from a Christian perspective. Physics of Einstein, if you're wondering what if none of this made sense to you, start with the Physics of Einstein. And I wrote that kind of on two levels. I have, the details of the Physics of Einstein are beautiful, and but I didn't want people to get bogged down with the details. So I put the details in boxes that you can either read or skip. So let's put it that way. So if you want to just skip the boxes, you can do that and get the basics of what Einstein discovered, or you can go through the boxes, and it's just high school algebra, but some people get intimidated by that too. So, but if you're adventurous, you can go through the boxes and see how the math works out. It's pretty amazing, really. And you can prove that E equals mc squared. It's just beautiful. It's really neat. And that's what makes atomic bombs work and things like that. The Importance of Genesis, again, is my brand new book that I didn't have 2 years ago when I was here. So if you haven't got that one, you might want to pick that up. And go check us out on our website, biblicalscienceinstitute.com. We're going to take a 10-minute break and come back with Q&A. So thank you very much. God bless.